HW12 Q1 Part B. Once again, we're asked to do some redox balancing. Let's start by assigning the oxidation states, which are kind of layups. Layups or gimmies. Starting with the chloride ion. It's alone and it bears a charge, so that charge is also its oxidation state. Chromium 3 ion, alone, bears a charge. Its oxidation state is also the charge. Chlorine molecule, diatomic, neutral. Oxidation state is 0. Now let's tackle the other compound. This is a kind of a fun compound. Dichromate ion. This is on your list of polyatomic ions that you know. Dichromate ion, Cr2O7, 2-. Definitely oxygen's the more electronegative. Chromium's oxidation state, well, we'll find it out as we go along. We have 2 atoms whose oxidation state is unknown. When added together with the 7 atoms of oxygen, whose oxidation state is known to be -2, should add together to the overall charge, which is -2. Little bit of math. We'll add 14 to both sides and divide both sides by 2 to get 6. So chromium's oxidation state within the dichromate ion is a +6. Oxygen's within the dichromate ion is a -2. Now we needed to do that just to figure out which element was oxidized and which element is reduced, and then from there we'll break apart into half reactions. So let's do some tracking. Chromium on the left side, +6. Chromium on the right side, +3. That's a decrease. So if it went from +6 down to +3, it could only have gained electrons, which means that element was reduced. Oxygen on the left side of the equation, -2, doesn't even appear on the right side of the equation. Don't worry about that. The process of redox balancing by the half reactions method will balance the oxygens. You'll see in the end we'll have a beautifully balanced equation in terms of both atoms of each type on either side and the charge. So it's not a concern for us right now that oxygen does not appear on the right side of the equation. Chlorine, -1 on the left side, 0 on the right side. That means it experienced an increase in charge. That's a good thing, because if one element is reduced, you certainly have to have another element that's going to be oxidized. So chlorine oxidized, chromium reduced. Let's break apart into half reactions. Chlorine on the left side of the equation was a Cl- ion. On the right side of the equation, it's the diatomic molecule chlorine, Cl2. Now that we have a half reaction, let's follow our steps for redox balancing. Step 1, balance elements other than H and O. Here, we need to balance chlorine. There are 2 chlorine atoms on the right side, so we need 2 chlorine atoms on the left side. Step 2 of redox balancing. Balance oxygen by adding water. There's no oxygen to worry about here. Step 3, balance hydrogen by adding hydrogen ions. There are no hydrogen ions to worry about here. Step 4, balance charge by adding electrons. Here we have to worry about something. We have on the left side 2 chloride ions. Together, that makes the left side of the equation -2 in charge. On the right side, we have a neutral species. In order to make the charge balance, you can only bring charge down by adding electrons. You can't take away electrons or bring the charge up in some way. You can only bring charge down. So in this case, we'll add 2 electrons to the right side so that now the charge count on the right side is a -2, which means that it matches what you find on the left. The charge on either side of a half reaction does not have to be 0. It just has to match what you find on the opposite side. Let's turn our attention to the reduction half reaction. The element reduced was chromium. On the left side of the equation, it existed in the dichromate ion. And on the right side of the equation, the chromium 3 ion. Step 1. Balance elements other than H and O. So let's start with chromium. I only see 1 chromium on the right side, but 2 chromiums on the left. That means we need the coefficient 2 on the right side of the equation. Step 2. Balance oxygen by adding water. Well, as you can see, we have 7 oxygen atoms within the dichromate ion. So that means we need to add 7 water molecules to the right side to make the oxygens balance. But by adding the 7 water molecules, that means we've added a total of 14 hydrogen atoms, which can only be balanced by adding hydrogen ions to the left side of the equation. 14 of them. You can see how this gets out of hand, right? Lastly, let's take a look at charge and balance charge by adding electrons. On the left side, as it's currently written, we have 14 species which have a single positive charge. We have 1 species that's double negative in its charge. So 14 minus 2 gives us an overall charge on the left side of positive 12. On the right side, we have 2 species whose charge is triple positive, and 7 species whose charge is neutral. 2 times a positive 3 gives us a positive 6. So there's an imbalance in charge. We need to add electrons to make it balance. We can only bring charge down by adding electrons. You can never take electrons away or in some other way bring the charge up. So the difference between 12 and 6 is 6, which means we need to add 6 electrons to the left side of the equation. And in doing that, we've brought the charge on the left side down from a positive 12 to a positive 6, which means the left side and the right side have charges that match. They're not 0, but they match. Now, we have 2 beautifully balanced half reactions. We're going to add them together, but in doing that, we need to make sure that the number of electrons crosses out. In the reduction half reaction, we have 6 electrons being gained, and in the oxidation half reaction, 2 electrons being lost. Lowest common multiple between 2 and 6 would just be 6. If we triple the coefficients of everything in the oxidation half reaction, we will arrive at 6 electrons, which means that we can cross out with what appears in the reduction half reaction. So I'm going to rewrite these 2 half reactions below, showing the same number of electrons on either side. We get to add the equations together, and crucially, the number of electrons crosses out. We'll just rewrite what we have overall. And since in this problem, the equation was balanced in acidic solution, we are going to be done. If they asked us to balance in basic solution, we would have to carry it just another step further. We would need to add hydroxide ions in order to cancel out the hydrogen ions. But as it is, we have a beautifully balanced redox reaction found using the half reactions method.